All right, hello class. Today we're going to go over 5.2, exploring quotients of rational functions. So today's lesson is more of an investigation and kind of getting you used to the steps that you can go through to figure out key features of rational functions. The next lesson, 5.3, will go into it in much more detail. So let's just start here by going over what a rational number is. So a rational number, so notice I'm saying number and not function. So we're going to differentiate between those two. So we know a rational number indicates the division of two integers. So that's anything like 5/6 and -7/8, right? Two integers being divided. So then what does it mean to be a rational function? So that means it is a function that can be expressed as f of x equals, and then p of x divided by q of x, where p and q are both polynomial functions. So basically just a polynomial divided by another polynomial. Keep in mind, because q of x is in the denominator, we always have to have our restrictions that tell us that the denominator cannot equal 0. All right, so for this example here, we have 3x squared minus 1 over x plus 1. This is an example of a rational function because a polynomial up top and a polynomial in the denominator. And notice we'd have to write the restriction that x cannot equal -1 because that's where the denominator would equal -1. This is also a polynomial divided by a polynomial, so it's a rational function. And because the only thing in the denominator is x squared, that means the restriction is just that x cannot equal 0. All right, this non-example here, this is not a rational function. So notice here, I'm going to kind of circle this. Okay, so this is a non-example. And it's a non-example of a rational function because even though there's a polynomial in the numerator, the denominator is not a polynomial function. That is a transformed square root function. Okay? So even though this function does have a restriction, right? We know the denominator cannot equal 2, right? That would make this equal to 0. It is still not rational. Okay, so just make sure you're looking out for that. All right, the next key feature that is common in rational functions are something called wholes. We touched on this a little bit last year, but not a lot. So for some of you, depending on your class, maybe you didn't go over this a lot. So a rational function will have a hole. So just as you can see in this graph here, see how there's a little hole here, meaning it doesn't exist at that one little hole. So if there's a hole at x equals a, that happens if the numerator and the denominator expressions both have a common factor of x minus a. So that means that if we factor the top and bottom, they both have a common factor that we can eventually cancel out. So if that's the case, that means if there's a hole at x equals a, that means when I sub in a to the top and bottom, it should produce 0 on top and 0 at the bottom. This is called the indeterminate form, and you're going to go over that a bit more if anyone takes calculus and vectors. So this is not a good form. We cannot have this. So what you have to do next is you have to try to factor and see if you can cancel out anything common. So for this example here, x squared minus 4 divided by x minus 2. At first glance, okay, first of all, I can see here x minus 2. I know that that would equal 0 if x was 2. So that's why I put my restriction x cannot equal 2. If you notice though, so I'll use black here, if I were to sub 2 into the top and bottom, so if I were to sub in 2 over here, so I'm going to do this over here, I would get, so f at 0, or sorry, my apologies, f at 2 would equal 2 squared, so 4 minus 4, all over, and then 2 minus 2. So that would give me 0 divided by 0. And like I said, that's called the indeterminate form, so this is not good. So that tells us that there is a common factor in the top and bottom. So we're going to try to factor where we can. So I notice that the numerator is a difference of squares. So I'm going to rewrite it as x plus 2, x minus 2. Once we've rewritten this here, I'm noticing that I have a common factor of x minus 2 in the top and bottom. So I'm canceling those out. And when I cancel that out, I am then left with just the linear expression x plus 2. And then I'm still maintaining the restriction. So x cannot equal 2 is still maintained because it has to continue from the beginning. Okay, so I always want you to think, even though you simplify expressions or cancel things out and it simplifies to something like this, which at first glance looks like a line, you can't forget that the equation had a past. Okay, so it had a past that had a restriction and that has to be carried forward. So if I asked you to graph this rational function, that means that it is going to be the line y equals x plus 2, but there is going to be a hole at x equals 2. There's going to be a hole at x equals 2 because there was a common factor of x minus 2 in the top and bottom. So when I draw my line, I'm going to have a slope of 1 over 1, a y-intercept of 2, as you can see in this blue graph here, and then there's going to be a hole at the x value too. So that's why there is a hole when I go up here. If you ever want to figure out what that y-coordinate is, a quick way of figuring that out is just sub that x value into the final equation here, and you will get your answer. Okay, so let me just kind of highlight that there. So when you're finding the corresponding y value, you always sub it into the simplified equation. So the equation after you've done your canceling out. So this kind of shocks a lot of people because you don't think that a rational function would look so basic, right? You don't expect a rational function to give out a shape of a line, but this is a case where it can. It produces a line with a hole in it, so that is the key feature. All right, so let's practice a bit more with that. So let's scroll to this question here. State the location of any holes in the following functions. So 2x minus 10 over x minus 5. So again, I always do my restrictions. I can see that based on the denominator, x cannot equal 5. If I were to sub 5 into the top and bottom, I would get 0 divided by 0, which is our indeterminate form. So again, this is a hint that I should be factoring. So let's start factoring the numerator. I can factor the numerator by taking out a GCF of 2. Okay, so we have 2 bracket x minus 5. X minus 5 is also a factor in the denominator, so I can cancel those 2 out, and then I'm just left with 2. Again, maintaining that restriction, so f of x is simplified to equal 2, where x cannot equal 5. So whenever I have an equation that's of the form y equals 2, we know that that is a horizontal line. So it's going to be a horizontal line at 2, and because we canceled out factors, that means we're going to have a hole at the number that made that factor 0. So since the factor was x minus 5, that means there's going to be a hole at x equals 5. Okay, so whatever the factor is, just change the opposite sign. And like I said, we're going to draw a horizontal line. So our graph will look like this. The horizontal line through y equals 2, and then I go to the x value of 5 right here. And I have a hole at that point. All right, let's try another one. So g of x equals, we've got a quadratic up top divided by a linear function at the bottom. Again, I use my restrictions to see that x cannot equal -4. A good thing to always do is immediately try to factor where you can, and that way you can easily see if there's any holes. So the minute that I see that this numerator is not in factored form, I'm going to put it in factored form. So that means it's a simple trinomial, so I'm looking for two numbers that multiply to -8 and add to 2. So that's 4 and -2. So x plus 4 times x minus 2 all over x plus 4. I notice I have my common factor. Those two will cancel out, and I am left with x minus 2. So again, I'm left with another linear function, a slope of 1 over 1 and a y-intercept of -2, while maintaining the restriction from its past that said that x cannot equal -4. Okay. So because I canceled out that factor, I know that there is a hole at x equals -4, and then I've got these key features to draw my line. If you are curious as to what the corresponding y value is for this x, so if you want to draw your hole first, that means I need to know what the y value is when x is -4. Remember, you're going to sub this back into the simplified version of the equation to find your y value. So I did g at -4. And remember, here we outline here for you, you're always going to the simplified version. Okay, so you're not going to the top one. Okay, that will produce 0 over 0. You have to go to the simplified one. And we get that there's a y value of -6. So I just found out, okay, that there is a hole at -4 and -6. All right, so when we draw that, it's going to be a line with slope 1 over 1, y-intercept -2, and as you can see, we have our hole at -4 and -6, right here. And that would be covering holes for rational functions. All right, let's move on to the next page. All right, vertical asymptotes. So how do we know when something has a vertical asymptote and not a hole? So a rational function will have a vertical asymptote. Right here, we'll have a vertical asymptote when the denominator is equal to 0. But you're probably thinking, well, in the previous example, when there was a hole, when you sub the number in, it equals 0. But the difference with vertical asymptotes is that there cannot be a common factor in the numerator and the denominator. So that means that it only makes the denominator equal to 0 when you sub it in. It does not make the numerator equal to 0. So an example of that would be here. So the vertical asymptote, there will be a vertical asymptote at x equals a if when you sub in a, you get some number in the numerator divided by 0. And that is called undefined. Okay, when you have any other non-zero number divided by 0, that's undefined. Therefore, it implies there's a vertical asymptote. So just making sure no common factor in the numerator and denominator is what makes it a vertical asymptote. So an example of that would be here. So f of x equals x plus 1 divided by x minus 2, where the restriction is that x cannot equal 2. So notice if I were to sub in 2 to this equation, I would get, here. So if I did f at 2, the way it is now, I would get 2 plus 1, so I'd get 3 divided by 0, and that would be undefined. Okay, so this is implying that there's a vertical asymptote. So it's not the case before where we got 0 over 0. So I notice that, I say, okay, the denominator, when does that equal 0? And that is how I can find my vertical asymptote. So x minus 2 equals 0 when x equals 2. So therefore, there's a vertical asymptote at x equals 2. And as you can see, this function would be graphed like this. So it will have those two L brackets, and it will have its vertical asymptote there. All right, let's try some more examples. State the vertical asymptotes of the following functions. So here we have the function x minus 1 divided by 3x plus 2. Right away, I know my restriction is x cannot equal -2 over 3. I can already see that if I were to sub in -2 over 3 to the numerator, it wouldn't produce 0. So this, when I sub that in, it would produce a number divided by 0. Therefore, a vertical asymptote is going to occur. So the first thing I would comment on is there are no common factors in the numerator and denominator, so therefore there are no holes. This is already in kind of good factored form, top and bottom, so I can already tell that. Then I would make note of, okay, that means there's a vertical asymptote wherever the denominator equals 0. I know that the denominator equals 0 at x equals negative 2 over 3, so that is my vertical asymptote, and that would just be my final answer. This one here, part B, 1 over, and then we've got our quadratic function. So what's hard for us to tell here is when the denominator would equal 0. That's going to be easiest for us if we put the denominator in factored form. So I tried factoring my simple trinomial, and two numbers that multiply to 5 and add to negative 6 are negative 5 and negative 1. So this is my nicer form because, as you can see, I can state my restrictions right away. I know that x cannot equal positive 5 and x cannot equal positive 1 from this. So I'm just looking here to get my restrictions here. So then I tell myself, okay, I know based on looking at it that there's no common factors, so there are no holes. And basically from your restrictions here, you can also tell what your vertical asymptotes are as well, wherever the denominator equals 0. So we get that there is a vertical asymptote at x equals 5 and x equals 1. Okay, now that we're done with holes, vertical asymptotes, now we're going to go on to horizontal asymptotes. All right, so a rational function will have a horizontal asymptote. Okay, and let's highlight this. Only when the degree of the numerator, p of x, is equal to or less than the degree of the denominator, q of x. Okay, please highlight that. Another way of writing that out in kind of little math short forms is what I have at the side here. So the degree, I use capital D, of the numerator, so a subscript n, when the degree of the numerator is less than or equal to the degree of the denominator. Okay, so you're allowed to, I use this notation a lot for short form. All right, so let's go through the two cases. Case number 1 is if the degree of the numerator is less than the degree of the denominator. Okay, so another way of writing this is how I've written it here in purple. dn is less than dd. Okay, so the function will have a horizontal asymptote at y equals 0 if this is the case. Okay, so that means if it's at y equals 0, that's another way of saying at the x-axis. So an example of that try and move this here. Okay. Would be this question here. So it's saying f of x equals 1 over x minus 1. So notice the degree of the numerator, because the numerator doesn't have a variable, it's just a constant. So because it doesn't have a variable, you assume the degree is 0. The degree of the denominator, okay, is 1, the imaginary 1 there. So that means degree of numerator is less than the degree of the denominator, and therefore you can conclude, okay, that it has a horizontal asymptote at y equals 0, okay, based on what was stated here. And an example of that would be at the side here, where it's just at y equals 0. Now, what about when there is case 2? Let me just get rid of that. All right, so for case 2, if the degree of the numerator is equal to the degree of the denominator, so say you have a linear divided by a linear function, quadratic divided by a quadratic, this is a unique case. So that means the function will have a horizontal asymptote at y equals a over c. Okay, so writing that in, y equals a over c. So what does a over c refer to? So A is the coefficient of the leading degree in the numerator. And C is the coefficient of the leading degree in the denominator. So what does that look like in an example? For example, here, I have f of x equals 2x divided by x plus 1. The degree on the numerator is 1, and the degree on the denominator is also 1. So that means their degrees are equal. And notice, you're always going to write this out, always write out this conclusion here. So that means I know there's a horizontal asymptote at y equals a over c. So a would be the coefficient of the leading degree here, so 2. Okay, so I'll highlight this here. Okay, so a is here. And then c is the coefficient of the leading degree in the denominator. So the leading term here would be x, and its coefficient is an imaginary 1. So that's why we do 2 divided by 1, which gives us 2. And that is why there is a horizontal asymptote over here at y equals 2. Make it a bit smaller. So those are your two cases. Always make sure that you are checking the leading degree. Sometimes the terms may be mixed up. It might say 1 plus x at the bottom, and make sure you rearrange it. All right, so let's practice that a bit more. So let's state the horizontal asymptotes of the following functions. So I can see here that the degree of the numerator is equal to the degree of the denominator, both equal to 1. Therefore, horizontal asymptote at y equals a over c. And a in this case is 1, c in this case is 3. So that means horizontal asymptote at 1 over 3. Y equals 1 over 3. For part B, I'm noticing that the degree of the numerator is 0 and the degree of the denominator is 2. So that means I have the case where degree of numerator is less than the degree of the denominator. And based on what we just learned, okay, that means that the horizontal asymptote is at y equals 0. Okay, so as long as you know those two cases. All right, next up is an oblique asymptote. So this is very unique. An oblique asymptote is an asymptote that is neither vertical nor horizontal, but is slanted. So we haven't seen these ones before. So when does this occur? So a rational function will have an oblique asymptote when the degree of the numerator is greater than the degree of the denominator by exactly 1. Okay, so that's very specific. So numerator is greater than degree of denominator by exactly 1. How do we find what this equation is? The equation of the oblique asymptote is going to be the quotient when the numerator is divided by the bottom. So this is going to take us back to our old units. So basically we're going to take one polynomial divided by another. We get a resulting polynomial, and whatever that polynomial is, that is the equation of our oblique asymptote. Okay, so let's look at this example here. It says x squared plus 4 divided by x plus 1. So the first thing I notice is that the degree of the numerator is greater than that of the bottom by exactly 1. It's degree 2, degree 1. So right away I know that my oblique asymptote will exist, and it's going to have the equation y equals and then whatever the quotient is. So sadly I'm going to have to do some work here. Okay, but it's everything that we know before. So let's start doing our division. We can do synthetic division here because the term that we have at the bottom here is linear, a linear term, a linear factor. So we can use synthetic division if you'd like, or you can use long division. So in this case here, our k value, right, if we were to use this, okay, So looking at our denominator, our k value is -1. If I put that on the outside, remember the inside here has to have the coefficients of the numerator, okay, the thing that's being divided. So the coefficient is going to be 1 for the x squared, 0 for the missing x term, and 4 for the constant. You guys know how to do your synthetic division. Bring the 1 down, multiply, add the 2. Take that answer, multiply by -1, put it here, add the 2, and we are left with 1, -1, and 5. Now remember, that just gives us the coefficient for x, the constant, and the remainder. So that means when we're done, our quotient has the equation x minus 1. So that is why my oblique asymptote is at x minus 1, which we have drawn in right here. So I know this is a lot of information to take in. As you go through more examples and as we go through more lessons, you're going to see it's going to come a bit more naturally to you. So just to kind of summarize what we've done so far before we try tackling some other examples, I just want you to make sure you go through these steps when you're analyzing a function. So step 1 should be to determine if there's any discontinuities, meaning restrictions. All right, so are there any discontinuities, aka is there anything that makes the denominator equal to 0? If you answer yes, okay, you then must ask yourself, is there a common factor in the numerator and denominator that can be divided out? If the answer is yes, that means there is a whole at x equals a. If there's not a common factor that can be divided out, that means there is just a vertical asymptote wherever the denominator equals 0. If there are no discontinuities, then that means there are no vertical asymptotes and no holes. Step 2. You want to determine if there are any horizontal or oblique asymptotes. So this all depends on the degree of the top and bottom. So if you have the degree of the numerator is lower than that of the denominator, based on what we just went over, that means there is a horizontal asymptote at y equals 0. If they have the same degree in top and bottom, that means horizontal asymptote at y equals a over c. If the degree of the numerator is higher by exactly 1, that means there's an oblique asymptote at y equals the quotient of those two functions. So hopefully you can refer back to this little chart here when going through to help you kind of organize your thoughts. All right, so like I said, let's try a bunch of examples. I usually give these as a few of you to do together, and then I have you kind of investigate the rest on your own, but I will go through them with you in this video. All right, so we are going to consider the following functions and identify the coordinates of any holes. So that means, remember, when we want to look for any holes, what's very important here is you want to look at the original version of the function. So the function before you simplified it. When you want to find the equation of asymptotes, that's when you want to look at the simplified version. Okay, so this is probably where students get confused the most, but like I said, we'll go through examples and you'll see what I mean. So our first one here is x squared minus 1 divided by x minus 1. Right away I know there's the restriction x cannot equal 1. I notice that the top can be factored as a difference of squares as x plus 1 and x minus 1. I see a common factor that can be cancelled out, so then I'm left with x plus 1 where x cannot equal 1. So let's start with answering our questions. So remember, you might have to do this work first before you can answer these. Okay. All right, since the common factor of x minus 1 exists in the top and bottom, that means we know there is a hole at x equals 1. Okay. So I made that notation. Now notice it asks for the coordinates of any holes, so that means I need to find the corresponding y value. Okay, so when I want to find the corresponding y value, that's when you have to sub it back in to the simplified form. Okay, so if you want to add at the side here, we're going to use simplified for the y coordinate. Okay. All right, so that means I am going to sub in x equals 1 into this simplified form here. Okay, so that's x plus 1. So that's going to be 1 plus 1. So that means I get a whole at x value 1, y value 2. Okay, so I've answered part 1. Part 2 is asking the equation of any vertical asymptotes. Okay, so because our final function, when it's simplified, is x plus 1, that means there's nothing left in the denominator that can equal 0. So that means there's no vertical asymptotes because the simplified version is linear. Part 3, there is no horizontal asymptote, again, because the simplified version was linear. All right, and we can exit there. And there is also no oblique asymptote as well. Okay, so no oblique asymptote, which I have over here. Again, because the simplified version was linear. Okay, so there wasn't anything to compare with the numerator being top and bottom. So our final graph should look like this. Okay. So it should have a slope of 1 over 1, a y-intercept of 1. So again, I'm going to highlight here, always referring to your simplified version. Okay. The hole is here, like we said, at 1, 2, and there's our line. Okay, let's move on to the next one. We have 3 over x plus 1. There's no factoring that needs to be done here. It's as simplified as it can get. We can see that x cannot equal -1 though right away. Oh, sorry, let's reveal this side first. Okay, so question 1 is, are there any holes? No, there are no holes because there's no common factors in the top and bottom. Vertical asymptotes, yes, because there is a place where the denominator will equal 0. So x plus 1 will equal 0 when x is -1, so therefore we have a vertical asymptote. Horizontal asymptote. We have a scenario where the degree of the numerator is less than that of the denominator, so therefore we know that means there's a horizontal asymptote at y equals 0. Okay, so 2 key features we can draw in. And lastly, there are no oblique asymptotes because we have degree numerator less than degree denominator. Okay. Remember, this would have to be higher by a degree of 1 compared to that one if that was the case. So, how would we draw this? Okay. So at first glance, I would just be thinking to myself, okay, I know it has, this vertical and horizontal asymptote. I draw those in. I'm also noticing here in this form, based on knowledge I have, that this looks like a transformed reciprocal function. So I do know it should have those 2 L brackets. If you're ever unsure if you're drawing it properly at this point, in the homework, I'm okay with you just subbing in some test points for x, and then finding corresponding y values. So all I did here was sub in some random x values to create other points, just to ensure that my L brackets were in the correct location. In the next lesson, 5.3, we're going to know how to draw this a bit more specifically. All right, part C. We have x plus 1 divided by x squared plus 2x minus 3. So the bottom is not factored, so that's why I'm going to factor that simple trinomial right now. So I factor it as x minus 3x plus 1. I have a common factor of x plus 1. And notice when I cancel those out, I'm left with 1 over x minus 3. Because remember, when you cancel something out, it's just like you're leaving a 1 in its place. So you leave a 1 here and you leave a 1 here. So it's still 1 over x minus 3. And that's a common mistake that students do. They usually cancel this out and then just say it equals x minus 3, and that's not true. It's 1 over. Okay. Notice here that even in my simplified version, so this is my simplified version, I still have the restriction that x cannot equal 3 and x cannot equal -1. That's because I'm always looking back into the original version. So the original version had 2 denominators, and therefore those restrictions have to be maintained here. Okay? Even though the bracket x plus 1 no longer exists in the simplified version. All right, so let's go through the questions. All right, we do know that there is going to be a hole at, oh, sorry, that got cut off. A hole at x equals -1 because of the common factor of x plus 1. To find the corresponding y coordinate, I'm going to sub -1 into this simplified version. I'm just going to highlight that again here. So I get 1 over -1 minus 3, so y coordinate of -1 over 4. All right, does it have a vertical asymptote? Yes, it does. That's because the simplified version still has a denominator, and I know that that denominator cannot equal 0. X minus 3 cannot equal 0, so therefore the VA is at x equals 3. So we've got a hole and a vertical asymptote. Next up, horizontal asymptotes. We also have that. So because the degree of the numerator in the simplified form, always looking at the simplified form, okay, the degree of the numerator is less than that of the denominator, means that we have a horizontal asymptote at y equals 0. So those are 3 key graphical features we just got. And we know there's no oblique asymptote because there is a horizontal one. Right, and you can't have both. It has to be one or the other. Okay, so what would that look like? We would have something like this. Our vertical asymptote, our horizontal asymptote, and our 2 L brackets. And please note that this little red dot here is the hole at -1, -1 over 4. So this one had one of each, which was nice practice. One of each feature other than obviously oblique asymptotes. All right, part D. Some of these might be special cases, and obviously we're just going to have to refer to Desmos for some of these, or just go ahead and start subbing in points like I did here in red to figure out more of what it looks like, because there are some that are a little unpredictable in terms of their shape. So that's why I wrote here, this is a special case, because we cannot simplify this any further. Notice the numerator and the denominator we can't fully factor. So what can we conclude here? So part 1, there are no common factors in the top or bottom, so therefore there are no holes. Part 2, we want to know when the denominator equals 0. So when does x squared plus 1 equal 0? That means I bring 1 to the other side, so it becomes x squared equals -1. If I try to solve for x by square rooting both sides, what happens is we get an error message. And that's because we can't take square root of negative number, so no x values exist, therefore no solutions, and therefore no vertical asymptotes. So this one has neither of the first 2 features. Part 3. I noticed that the degrees are the same in the top and bottom. They both have degree of 2. So that means I know I'm going to have a horizontal asymptote at y equals a over c. So a in this case is the number 2, and c is the imaginary number 1 in front of the x squared at the bottom. So horizontal asymptote at 2 over 1. And because there's a horizontal asymptote, there is not an oblique one. Right, because that means the degrees are the same. Oh, sorry, let me just fix that there. The degree of the numerator is equal to that of the denominator. So that should be a D there. Okay, so then what are we supposed to do with graphing this, right? We don't really have much to go off of. All we know is that it has a horizontal asymptote at y equals 2. So you can use Desmos in this case, or you can do like I said here, plug in some random numbers just to get an idea of what's happening. Okay. And this is what the graph will look like, which is pretty cool. So that's why I meant that some reciprocal functions are really unpredictable in terms of their graphs. Okay. So here we've got our horizontal asymptote, and we've got this cool shape here. So it has no restrictions on x, which is cool. All right, so let's move to the next page. Again, normally I would be having you guys investigate this on your own, but I am going through it with you now since we can't go through it in class. All right, let's try part E, 0.5x squared plus 1 divided by x minus 1. So I know that my restriction is that x cannot equal 1. So let's start off by taking out a GCF. Again, you're always trying to factor, see if you can factor. Even if you try to take out a GCF, it may not help you in the end, but it's always good to do that as your first step. So I take out 0.5, and that just leaves me with x squared plus 2. So unfortunately, that just showed me I can't factor this or this. This is already factored. I can't factor this any further. So step 1 is telling me that there are no holes. Okay, because there are no common factors. I'm just going to say part 1. There are no common factors in the numerator and the denominator. Okay. Part 2, that's when we want to know when the denominator equals 0 if there's any vertical asymptotes. So the denominator is x minus 1, and that would equal 0 at x equals 1. So that is my vertical asymptote. The degree of the numerator, so this is one of the special cases, is greater than that of the denominator. So therefore, there's no horizontal asymptote. Okay, this is a special case where because the degree is greater than the bottom by exactly 1, that means there is going to be an oblique asymptote. Okay, I know everyone is very excited about this. So let's practice finding that. Remember, that just means I'm going to go back to the original question, okay, and I'm going to take x minus 1 and divide it into the numerator. Okay, and again, the denominator is linear, so I can use synthetic division. So because the denominator, because x minus 1 would mean that there's a k value of 1, I put that on the side, and I get these numbers from my coefficients. 0.5, 0 because there's no x term, and 1 for the constant. I do my synthetic division, and I end up with a quotient of 0.5x plus 0.5, and then obviously we have our remainder here. So that means I concluded that there is an oblique asymptote at 0.5x plus 0.5. Okay? Or you can write that in fractional form. So 1 over 2x plus 1 over 2. And this is what the graph will look like, which is pretty cool. Okay, so notice, vertical asymptote. In purple, we have our oblique asymptote. And then notice we kind of have, it looks like our L brackets were squished a little bit, right? They don't look like L's anymore, and that's because of the slanted asymptote. So you're probably wondering, well, how did I know that they would, that those two kind of shapes would go here and here? That's why, if you notice at the side here, I just tested some numbers. So for example, I said, okay, what is the y value when x is 0? So I subbed it in, and I got a y value of -1. So that's how I got this point here. That was a hint to me that then one of the shapes was going to be here. And then they're typically always opposite each other, so that means the other one is over here. Okay, so like I said, sub in numbers, see what happens. Or in cases like this, you can verify with Desmos. All right, part F, x squared plus 2x over x plus 1. Okay. All right, so we first try to factor. We can take out a GCF of x. Unfortunately, that does not help us to see any common factors, but always factor first in case. So always good practice to do this. There are no holes. There is a denominator. The denominator would equal 0 when x is -1. So that is my vertical asymptote. There is no horizontal asymptote because the degree of the numerator is greater than that of the denominator. There is an oblique asymptote yet again because the degree on top is greater than that of the bottom by exactly 1. So that means you would have to do your synthetic division again. This time your k value at the side is -1, okay, because the denominator was x plus 1. Our coefficients here, notice the top has a coefficient of 1, 2, and then the constant's missing. So that's why we have 1, 2, and 0. We do our synthetic division. All right, and we remember this is for x, this is the constant, and this is the remainder. So we get, sorry about that, the remainder. So we get a quotient of x plus 1. So we've got oblique asymptote, vertical asymptote, and no holes. Notice that this one is similar in shape to part E, but except now those two brackets, okay, that have been a little misshapen a bit, now those two brackets are on the opposite areas. So that's why I said it's important when you get a case like this to sub in random x values. So again, I subbed in 0 into the equation, okay, and I got 0 back. So that's why I plot this point 0, 0. That was an indicator to me that the shape was going to exist in this area. And if it exists here, it's most likely that the other bracket will exist opposite it. All right, and our last question, another special case is this one, 9x over 1 plus x squared. So in this case here, like I said, I would expect you to use Desmos to verify. Excuse me. I can see it's fully factored, no common factors, so no holes. There are no vertical asymptotes because 1 plus x squared, when you set it equal to 0 and solve for x, gets you to that similar situation where you can't square root a negative. So there are no VAs. The degree of the numerator is less than that of the denominator, so I do know that there is a horizontal asymptote at y equals 0. And because there's a horizontal asymptote, automatically means there's no oblique one. So the final graph of this one is going to be cool. Look at this. Okay, and this is what our graph is. Okay, so it should be kind of going through there. All right, so this one again is kind of a funky shape. It kind of has that somewhat odd symmetry a bit there. But again, you can use Desmos to get a clearer look at this picture. And as you can see, I know you're probably confused. Why are we going through the horizontal asymptote? There are cases in some functions where you can cross through a horizontal asymptote, typically at one key point. Okay, and this happens because if I were to sub in 0 here, okay, I would get 0 divided by 1, which is equal to 0. So 0 divided by a number is 0. So that's why there's a unique case where it can cross here. However, it cannot be crossed at any other point on the horizontal asymptote. And that is one of the last special cases I wanted you guys to see. All right, that was a lot of information for 5.2. Keep in mind that there aren't too many homework questions here, as you can see. And then you can move on to 5.3, where we will go over similar stuff again, but in more detail. All right, good luck, guys, with the homework, and let me know if you have any questions. All right, take care.